In the previous two lectures, we had started the discussion on the different kinds of RF diodes and their applications. However, diodes are not sufficient to cater to all possible applications of RF where active devices are involved. The simple example is amplifiers. You cannot amplify anything using a diode. So, for amplification purposes, you will need to make use of transistors. And where transistors are concerned, there are basically two types: bipolar transistors and field effect transistors. So, from your circuits course, you will already be familiar with both. So the field effect transistors are also called as MOSFETs. You will be familiar with the basics of both of these devices. One is a current controlled transistor and the other is a voltage controlled transistor. So as far as RF is concerned, we are interested in working with these transistors at very, very high frequencies. Let us say of the order of a few gigahertz. So, therefore, the idea is which among these two transistors, or the question is which out of these two transistors would be better suited to work at high frequencies. Well, if you were to make a bipolar transistor and a MOS transistor in equivalent technologies, you would see that the bipolar transistor would work at higher frequencies, or rather, the bipolar transistor or the BJT would have more bandwidth compared to an equivalent MOSFET. Why? Because the MOSFET has a number of parasitic elements in it. In particular, parasitic capacitances which limit its bandwidth. But that is not the end of the story. One of the biggest advantages of MOSFETs is that if you reduce their size, they retain their properties. And if you keep reducing their size, those parasitics also start reducing, and therefore the bandwidth improves. Now that process of reducing the size is called as scaling. That is called as scaling. So the most powerful tool that today's engineers require is provided by MOSFETs. They are giving us a wonderful opportunity of allowing us to reduce their size and at the same time retain their properties, if not improve them. At the same time, we are getting more bandwidth out of those. So therefore, that is the very basic principle behind the field of VLSI, getting to integrate more and more number of devices on the same single wafer of silicon area, thereby getting more work done per unit area of silicon. So therefore, we shall focus on MOSFETs. Now, the theory of MOSFETs, all of you are very well aware of. I shall not get into too much of detail with those. Rather, I shall revisit some of those concepts which are important from an RF perspective. So, as all of you know, a MOSFET is made from a p-type substrate with two layers of heavily doped n-type semiconductor. So a MOSFET is a 4-terminal device. So the 4 terminals are called the gate, the drain, the source, and the body or bulk. So the MOSFET that is made using a p-type semiconductor is called as an NMOS. This shaded area is silicon dioxide, which is an insulator, and the gate material is conventionally a metal, but more recently people are using polysilicon. So one of the most important parameters of a MOSFET is its threshold voltage, VTH. So therefore, the gate voltage must be able to create a free field that causes inversion inside the p-type body, and that for that inversion to happen, its effect must be stronger than the effect of threshold voltage. So effectively, for the channel to form, both the gate to source voltage and the gate to drain voltage must be more than VTH for channel to form, right? So this is the bare minimum requirement. Now there are various characteristics of our MOSFET which you may be familiar with. Before we discuss those, the symbol for a MOSFET is like this: gate, drain, source, and body. So by controlling the gate voltage, we can control what is the current that flows from the drain to the source, and that current is called as the drain current ID. Now for NMOS, the body terminal is usually connected to the lowest voltage. The lowest DC voltage in the circuit. And for the PMOS, where the body is N-type, the body is connected to the highest possible DC voltage in the circuit. This is done so as to not allow any kind of parasitic diode inside the body to be forward biased. Notice that the P-type over here and the N-type here and here, they have the possibility to form a parasitic diode or two parasitic diodes. So therefore, so as to not allow any kind of parasitic diode to be formed, this body connection is extremely important. Otherwise, the diode may draw some current. Now, you may know that if I were to draw a plot of the drain current ID versus the gate to source voltage, until VTH, there would be no current. After that, the current would increase something of this kind. So this region is called as the cutoff region. And the MOSFET is not of much use in this region. However, we know that the drain current depends directly on VGS, or the gate to source voltage. So if I were to now draw a plot of ID with respect to VDS, that is the drain current with respect to the drain to source voltage. This is also called as the output characteristic. So you will see that initially the drain current would rise something like this and then go in this format. This is for keeping the VGS constant at some value, VGS1. If I now increase the gate to source voltage and keep it constant at some higher value, So what I would see is something like this. So in this region, you can see that the dependency of ID on VDS is kind of in a quadratic nature. That means it is dependent in the second order with respect to VDS. So over here, it is also seen that the ID has a linear dependence on VGS. So therefore, this region is also called as the linear or triode region. Now, once you cross the linear region, the variation of ID with VDS is lesser. Ideally, it would be something like this. It should be flat with respect to VDS. So VDS plays absolutely no role in choosing ID. These curves would have been flat. So therefore, this region is called as the saturation region. So in each of these regions of operation, the drain current can be written in two different ways. I think this is the one. Yes, I believe so. So as you can see, ID depends linearly on VGS and quadratically on VDS. And in the saturation region, in the ideal case, there is no dependency on VDS. So therefore, it looks like this. However, we saw that there indeed exists a small slope where ID changes weakly with VDS. So therefore, that effect is actually called as channel length modulation, and it is indicated by a parameter called lambda. So now you see this ID is dependent linearly on VDS, where this lambda is the channel length modulation parameter, which is quite small. But nonetheless, it's very, very important. With this, we can actually try and make a small signal model of the MOSFET, which you are already aware of, for the low frequencies. So as you know, if you neglect the body because it is connected to a fixed voltage, the small signal model essentially treats the MOSFET in such a way that it is DC biased in a proper way, and the AC voltage is so small in magnitude that it does not affect the bias conditions in any way. So before we actually discuss about the small signal model, it is important to choose which out of these two regions we must investigate. In the linear region, what you see is that for a small change in VDS, there is an appreciable change in ID. So here what is happening in the linear region, the resistance between the drain and source is very, very small. Whereas in the saturation region, for a large change in VDS, there is a small change in ID. So therefore, the resistance in the saturation region is much more. Therefore, we can also say that because the current changes slowly with VDS, here the transistor can act like a constant current source. The constant current source in the saturation region. And that makes it a very good candidate for being used as an amplifier. So therefore, we shall focus on the saturation region. Now, over in the saturation region, to see how well the transistor is able to act like an amplifier, we need to see how much is the change in current with respect to the change in the input voltage. So therefore, we define a quantity called as transconductance, GM, and that is nothing but a ratio of the change in the drain current with respect to the change in the gate to source voltage. Why these two? Because the gate to source voltage is the control element and the drain current is the quantity that's being controlled. So therefore, we define it in this way. A partial derivative considering VDS is constant. So here what is happening is we can almost say that for small AC signals, the drain current, which I will now write in small I. This small I indicates AC, capital I indicates DC. So this is almost equal to GM times VGS. This is considering only the AC components. So therefore what I can say that this is my gate, this is my drain, and this is my source. So it's three terminals. The body I am not considering at this point of time. So the gate is isolated from both drain and source. That is, there is no connection because of the oxide layer. So therefore, I'm just going to show it in this way. There is no connection whatsoever between the gate and source, between the gate and the drain. Now, we can define something over here which is called as the small gate to source voltage VGS. And we can define our drain current using a dependent current source, and we can define it this way, which is GM times VGS. Now in the saturation region, as I said, the drain and the source, between them there is a very high resistance, also called as the channel resistance or the drain to source resistance. So this RDS can be defined as the ratio between the change in drain to source voltage with the change in drain current. So therefore I can say it like this: 1 by RDS is actually equal to D differential of ID with respect to differential of VDS for constant VGS. So therefore, if lambda is 0, the RDS will tend to infinity. But if the lambda is finite, the RDS would be also a finite value. Ideally, we want it to be large. Usually, it's of the order of a few kilo ohms. The more, the better. So therefore, between the drain and the source, we have this thing called as RDS. So this is the very basic small signal model of a MOSFET. And this is what you have learned to be valid for low frequencies. Now, with this knowledge in mind, let us proceed to see how we can modify this model, the existing model, to account for RF frequencies. Now, as I was saying a little earlier in the lecture, that one of the reasons why conventionally the MOSFET was thought to be having less bandwidth is because of many parasitic elements. Let us look at some of those parasitic elements. Let us consider the phenomena of inversion. Now, inversion is the phenomena which we call for channel formation. the basic idea of channel formation. So let us say that this is my NMOS, the body is grounded, this is the source, this is the drain, this is the p-type body, and this is my gate. Now let us say, for the sake of simplicity, that Vs is 0 and Vd is also 0. That is, the source and drain are both grounded. And my Vg is something that is more than Vth. In that case, what would happen is that a channel would be formed which looks like this. So it would consist of electrons. It's kind of like a bridge that connects the source and the drain. Now, what you will actually see is that, suppose we define that this is called as L. So L is the channel length. And also the gate from the top may have some width, let us call it as W. But all said and done, when the inversion happens, when the gate voltage exceeds the threshold voltage, this channel is actually uniform in nature. Now what is happening over here? You have a plus voltage and you have negative charges over here, and the two are separated by this oxide layer, which is SiO2. Let us say the thickness of the oxide layer is Tox. Then we can think of this as a capacitor, and this is called as the gate to channel capacitance, CGC. The gate to channel capacitance. Now, what is this? Can we model this? So the gate to channel capacitance essentially looks like this: the permittivity of the oxide times the gate area, which is nothing but W times L, divided by the distance between the two plates, which is nothing but Tox. This is what is called as the gate to channel capacitance. Now, this is a very idealistic case where the channel is uniformly formed, but in reality that does not happen, and we are going to see why. But before we see that, let us try to model this capacitance in a slightly different way. We have essentially modeled this capacitance as a big single one that exists below the metallic layer. So rather than doing this, what we will do, we will kind of draw a line of symmetry over here, and the left half we will call it as with respect to the source, and the right half we will call it with respect to the drain. So what we are essentially doing, we are kind of looking at this CGC, the gate to channel capacitance, as a parallel combination. Let's call this as gate. This is the channel. We are looking at it as a parallel combination of two smaller capacitances. So this is called as the CGS, and this is called as the CGD, or the gate to source capacitance and the gate to drain capacitance. So what is the relationship between CGS and CGD? Well, looking at the symmetry of the situation, they should be equal. So CGS equals CGD, and that is equal to half of CGC, because CGC is nothing but a parallel combination of these two. But this is only for ideal inversion. That is, when the source and the drain are at the same voltage. So when the source and drain are at the same voltage, there is no drain current. And that is useless for us, because we want there to be some drain current. Otherwise, the notion of the MOS being able to amplify is meaningless. There is no meaning of it anymore. So therefore, let us look at the channel in saturation region. Let us look at the channel in the saturation region. Channel in saturation region when the drain current is non-zero, and that is what we want. So let us say this is our substrate, this is N plus, this is also N plus, this is P sub. Let the body be grounded. Now let us suppose Vs is 0, Vd is some non-zero finite value, and obviously Vg is there. Now you see the situation is slightly asymmetrical. On one side, you have the source voltage is 0. And here you have the drain voltage, which is non-zero, and in the middle we have the gate voltage. So therefore, because the gate to source voltage is now quite large and the gate to drain voltage is smaller, what will happen immediately we can say is that because the drain voltage is now non-zero, the channel will carry electrons from the source to the drain. Thereby, the drain current will flow from the drain to the source. But more importantly, what will now happen is that because of this variation in the two potentials, on one side, more charges will accumulate. When I say charges, I mean more electrons. There's a strong positive field over here and a weaker positive field over here. So more charges will accumulate on the left hand side as compared to the right hand side. So therefore the channel will now look slightly tapered. So more charges, electrons are anyway here. So more electrons will accumulate here and less electrons will accumulate here. So therefore, if we were to again look at the left half versus the right half from the capacitances, we can immediately say that because less charges are over here, the capacitance on the right hand side will be lower. So therefore, a more realistic view as compared to the ideal inversion is that the CGS is more than the CGD. This is for sure, because lesser charges will accumulate on the right hand side, more charges will accumulate on the left hand side. So therefore, the exact way to analyze would be really complex. What is now CGS and CGD? So in the ideal inversion, we had said that each CGS and CGD are equal and equal to 1/2 of the CGC. So now a more better approximation now will be CGS is 2/3 of CGC and CGD is 1/3 of CGC. That makes CGS equal to twice of CGD. And this is a pretty accurate and good approximation which works out for most of the cases. So CGS is now more than CG because of asymmetric channel. So with this, let us now modify the small signal model which we already know. So now the question is, why are we including these capacitances here? Why then did we not include these capacitances for our low frequency also? Well, we could have included. Nothing stops us from including. But what happens is these capacitances, the CGS and CGD, are really small. So therefore, at low frequencies, these capacitors behave almost like open circuits. So therefore, that makes our life a lot more easy. But as the frequency is increased, and we come more and more into the RF range, the capacitances start playing a role. Because now as the frequency is higher, we cannot simply brush away these capacitances by calling them as open circuits. They will have some finite reactance. So therefore, at RF, these play a more important role. So therefore, we had said this is the gate, this is the drain, this is the source. So we had said this is what it looks like. VGS is over here. This is GM VGS and this is RDS. So now let us incorporate those capacitances which we talked about. The gate source capacitance would be over here. This is CGS. And we will also have a gate drain capacitance over here, which is CGD. So this is the modified form of the small signal model for RF. Is that it? Is that it? Well, not quite. Not quite. There is a small thing that we are missing, and that is the effect of the body. So what we had said was that we shall connect the body terminal to such a voltage so as to put those parasitic diodes or PN junctions in the maximum possible reverse bias. But many a time that may not happen. Let us again look at the NMOS. Now I am not showing the gate voltage because right now it would not play much of a role. Now suppose this is the p-type body and somehow the body voltage becomes more than the source voltage, or the body voltage becomes more than the drain voltage. In that case, what will happen? There are two PN junctions, one over here, the other over here. There are two p-n junctions, one over here, the other over here. They will start behaving like forward bias diodes. So essentially there will be two parasitic diodes which looks like this. I'm showing in dotted. One over here and the other over here. Two parasitic diodes. So therefore, some current may flow here. Let's call it as IBS, that is body to source. Some current over here, let's call it as IBD, or body to drain. Now what you notice is that without using an insulator, the body terminal is also able to cause some current that looks to be flowing between the drain and the source. So this is also called as the backgate effect. Backgate, why? Because the body now kind of behaves like a pore gate, but causing a very similar effect. Now suppose VD is more than VS, then what will happen? In saturation or in any on condition, the drain current will flow from here to here. So if VD is more than VS, which of these two currents will be higher? Obviously IBS will be higher, because VBS is higher and VBD is lower. So therefore IBS will be higher than IBD. So for an outside person, what they are seeing is that the main drain current is flowing through the channel, and also there are two currents in opposite directions between the drain and the source from below. So since IBS is more than IBD, I can say that overall there is one more current which is flowing from drain to the source, because IBS is more than IBD. So this is called as the backgate current. And now, just like how we had derived or how we had defined something called as transconductance GM for the normal mode of operation, there is a definition for this backgate current also, and that is what is called as the backgate transconductance or the body transconductance. That is GMB. And effectively, since there are two currents, one main drain current and the other through the body effect, we can think of it as another component of the drain current itself. So therefore, this is defined in this manner. The derivative of drain current with respect to it will be the other way around. And for constant VDS. Just like the previous case. So now what would happen is that the model would again undergo a slight modification. So far what we had done, this is the gate, this is the drain, this is the source. We added one capacitor over here, one over here, CGS, CGD, this is VGS, this is GM VGS, this is RDS. Now what we will do, we have to account for this current also, the backgate current, which looks like this, the small signal backgate current, which is GMB times VBS. This is another modification. This is another modification. Now, what we have done, we have taken the existing small signal model as a starting point and have talked about some of the high frequency effects and non-ideal effects also, and have made a slightly more detailed model. So, in addition to this, there are two more capacitances also. Let us see what they are. Now, suppose we are successfully able to mitigate the body effect by properly reverse biasing the body and the source and drain parasitic diodes. We are still not in a good position. Let us say this is the source and this is the drain. This is the body. So when the body and the source are reverse biased, what will happen is that essentially there will be a capacitance that exists between this junction. Because this will now form a depletion region. Likewise, if the body and the drain is reverse biased, there will be one more parasitic capacitance between these two. And that you can find out pretty easily just by knowing what is the thickness of the depletion region and the surface area of the source and the drain that is touching the body. So therefore these are called as C, BS and C, BD, or the body to source capacitance and body to drain capacitance. So therefore, how would the complete model look like? So if you were to define another terminal called as the body terminal over here, you will find this capacitance, which is CBD, and one capacitance over here, that is CBS. This is the complete small signal RF model of the MOSFET. We shall continue from this discussion in the next lecture. Thank you.